Hello world, it's Siraj and welcome to this live stream. Today we're going to be generating MNIST images with a variational autoencoder. Now I know what you might be thinking. MNIST, not again. Please, no MNIST. You might be thinking, just screw this. You might be trying to get out of the live stream, but I'm telling you stop. Okay, because this is not about MNIST. This is about something much cooler than MNIST. This is about generative models, specifically my current favorite type of generative model, the variational autoencoder. Okay, this is gonna be dope. We can even generate Pokemon with this, okay? And we're gonna look into that. So sit tight, because that's gonna be dope. Who doesn't wanna make Pokemon? I do, okay? So hi everybody, thanks for coming in. I'm gonna start off with a 2-minute Q&A, and then I'm gonna go right into the code, okay? I've got this IPython notebook, Jupyter notebook, and it's got the images in there, but I'm gonna be coding all of it live. And yeah, so it's gonna be awesome. So let's get down to business to defeat determinism. Okay, so do we have any questions? Because I love answering them. All right, so any questions about AI, machine learning, deep learning, all of it is all good. You know, so just throw them at me and I will definitely be the person to answer them, okay? So, hi everybody from Colombia and India and Pokemon and Hyderabad and all over the place. We have over 150 countries represented in this community, and we almost have 100,000 subscribers, making us the largest AI community in the world. So it's a huge deal right now. We are making history. You guys are a part of history. So Matt Campwell asks, can you cover or maybe mention clustering? So that's a great question. In this course, this is a part of a course. Remember guys, this is a series of data points, of knowledge that we are building off of over time. And so right now we are finally on unsupervised learning. So what is one technique to learn from data that without labels? Clustering. So for clustering, we are going to talk about clustering at the end. Yes, we'll talk about clustering. Not like k-means clustering, which is the most popular type, but we're talking about clustering in an embedded space. Okay, so that's clustering in terms of the latent space. That's what we're gonna go over. So one more question and then we're gonna get started with this, okay? So Akshay Bhatia asks, thoughts on Cafe 2? Okay, so here are my thoughts on Cafe 1 through 5. No, just no is my thoughts on it. Don't use it. Use TensorFlow, use PyTorch. Don't use Cafe. Why? Because Cafe makes you define models through what are those, like JSON files? No, you wanna define your models programmatically. Why? For modularity, because you wanna call them through different parts of your code. You don't wanna just define some static file that you then have to go into, and there's not a lot of reusability with Cafe. Internally within Cafe, there's a lot of reusability, but you can't really use it with other frameworks as easily because it's not programmatic. Okay, so that's it for the questions. Actually, one more. This is actually a very good question. Could autoencoding be usefully applied to generate genomic sequences? Yes, absolutely, you could, absolutely. Because remember, an autoencoder, and we're gonna talk about this, reconstructs the input data. So so you could reconstruct genomic sequences, but you could also generate novel genomic sequences. Have you seen the movie Jurassic Park? We could make that happen. I'm dead serious. We could generate DNA sequences of velociraptors and T-Rexes by reading data sets of current mammals and then extrapolating, or what's the reverse of extrapolating, back into the past and trying to find those base pairs from which everything else sprung up from. So there's a lot of cool stuff coming, okay? So we are just at the beginning of this. Let's get started, okay? Okay, GANs are coming next. So let's get started with this. We've got 333 people live, so this is gonna be amazing. Let me make this bigger. So generative models model a distribution of data over high dimensional space. What does that mean? So this image is a little weird because it starts with Z. So Z is the latent space. So what do I mean by that? Z is after we've encoded some data, we have then represented it in some right? We have a representation of some high dimensional data. And what do I mean by high dimensional? Well, even an MNIST digit image is 784 dimensions. So these dimensions are pixels, right? 784 because it's a 28 by 28 image, right? So 784 dimensions. We've taken this 784 dimensional data point, and we've compressed it into a lower dimensional space. So that could be like 10 or 12 or 20 dimensions. It's a representation. But what happens when we compress data always? There is some loss of that data. It's lossy. So we take that lossy small dimensional representation and we reconstruct the original input with this yellow part, right? So this is Z, so it's already been encoded into Z, and then we decode it, and then we create a generated distribution of this data. Okay, so what do I mean by that? So let me say two things. The first thing is that latent is the same as embedding. It means the same as hidden. Okay, these are just when it comes to stochastic models, when it comes to generative models, only now do we start using the word latent, because I don't know, Bayes just like the word latent, but it means the same thing. Don't be confused. Latent, embedding, hidden, it means the same thing. Okay, so then distribution. What do I mean by distribution? Right, you can think of a 2D distribution. A 2D distribution is that bell curve, right? It's a Gaussian curve. So that's a 2D distribution. But how do you what even is a distribution in general? A distribution is a realm of possibility. Okay, it's a realm of possibility. What are all the possible values that some piece of data can be contained in? What is the wall that it can be contained in? And that is what a distribution is. A high dimensional distribution represents the realm of possibility of all the values from some data set, okay? So we have some generated distribution versus the true data distribution, which is what the actual data that we're training on, what is the real distribution of that data versus what we generate. And we're gonna use a loss function that I'm gonna define that's gonna minimize the difference between those two until they are indistinguishable from each other. And this word indistinguishable is used in variational autoencoders, and it's used in generative adversarial networks, which I know you guys are super excited to go into. I am too, and we're going to go into those, but we've got to get our variational stuff down first, okay? The name of the game is stochasticity, okay? Non-deterministic randomness, okay? There's so much cool stuff we can do once we start getting into this, okay? So autoencoders are a type of generative model, okay? And so a regular autoencoder looks like this. It's boring, it's plain, it's simple, but you can use it for a lot of cool things, but just comparatively, compared to variational autoencoders, they're not as cool. So it's a 5-step process, right? We start off by initializing our weights randomly. We always randomly initialize weights. And then we do a full forward pass through the batch, through the encoding and then decoding. So we could just think of both neural nets. An autoencoder there are two neural networks, right? An encoder and a decoder. But when we do a forward pass, for all intensive purposes, we just think of it as one big ass neural network, right? We start at the input and we get to the output by performing a chain of computations, right? It's just matrix multiplication at every layer until we get an output, right? And then we construct a loss function via MSE, which means mean squared error, of the original data to the reconstructed data. What is the mean squared error? It's a very generic loss function used a lot. It's used a lot. And it just means take the output versus the expected output, find the difference between those two, so subtract it, and then add up the difference between all of your input-output pairs divided by the number of them, and then those differences, you square them, divided by the number of them, and you get the mean of the squared error, okay? So it's a very simple formula, and then we calculate the gradients using backpropagation, okay? That's autoencode. Those are autoencoders, but right now what we're going to do is, you guys are hilarious. Okay, I love you guys. Okay, so those are autoencoders, right? So now we're gonna turn it up a little bit. Okay, now we're going into variational autoencoders. So what are the problems with autoencoders? They have so many problems. 99 of them. No, that's Jay-Z. So problems are they will overfit unless you have a large training data set. So this actually applies to all neural networks. All neural networks will overfit until you have all generic deterministic neural networks that we're used to, that we've been talking about. They will all overfit unless we have a lot of data. So how do we prevent this? How do we prevent overfitting? There's another problem. The gradients diminish quickly, so weight updates get progressively smaller the farther we go from the output, the vanishing gradient problem. And now, if you can remember, and here's a pop quiz for you, How do we solve the vanishing gradient problem for recurrent networks? I'll give you 5 seconds. 5, 4, 3, 2, 1. LSTM cells, right? LSTM cells, GRU cells. Why? Because they capture gradients over time, because we were backpropagating through time, and we use these cells to not have that gradient vanish. But there's another way that we can solve this. The solution to both of these problems is to add a variational component to regularize training. What do I mean by regularize? To improve training. So the variational component is we add some kind of random distribution inside of that, and we're gonna go through this mathematically. So I'll go into detail about what I'm talking about. But we start off with an input x, and then the input's gonna be some image or whatever. And then we say, what is the probability of z given x? So what is the probability of this hidden state value given x? And it's going to give us this hidden state. And then we take the hidden state and we say, what is the probability of the output x given this hidden state? And that's going to give us our output. And this little 3D dimensional badass looking curve thing is what we're gonna code it. We're gonna code, okay? So they were introduced 3 years ago. They're built on top of standard function approximators, neural networks. By the way, neural networks are considered universal function approximators. I haven't actually said that in this course, by the way, but they are. What do I mean by that? Given any set of inputs and outputs, you have some function, right? You have some relation, some mapping between this data, right? Like the simplest one that we could think about is y equals mx plus b, right? The f of x equals, or y equals mx plus b. There's a relationship between y and x, and the function is mx plus b. But neural networks can find a function, a mapping between any sets of input-output pairs. And so they're amazing, okay? So let's go ahead and get started with this. Not LSD, LSTM. Although, anyway, let's just get into the code, guys. Where were we? So let's just get started with this. Oh, and I've got some badass examples here. I didn't actually show those examples. But we can generate Pokemon. So this dude... Remember, by the way, we got to get away from this MNIST stuff, guys. I mean, if you look at the NIPS papers from 2016, the most used data set by far was MNIST. But what would be better as a standard like base format? Pokemon would be better. Not the new stuff. I'm talking about the original 150 Pokemon that everybody knows and loves, okay? Use those. Why? Because when we are using generative models, we can generate new Pokemon that are a fusion of the ones that already exist. So this guy tried it out over here, and I have links to this in the notebook, so check it out. So these were the original, and these were the reconstructions. So the reconstructions were clearly terrible. It was a very bad job. But the point is that he tried. So that was awesome. So check out that repo, for at least for the data set. And then one more example. We can generate faces as well. Now this is the second most used example for both generative adversarial networks and for variational autoencoders, generating faces. So this Frey faces manifold it's like the data set for generating faces. You can do that too. Okay, so those are two examples, and let's just get started with this code, all right? So the first step is for us to import our dependencies, because we have only 3 that we're going to use. Hard mode is not on because hard mode in this case would actually be a lot of code. And then what do I mean by hard mode? I'm talking about using just NumPy. We're going to use TensorFlow, okay? And that's the name of this live stream, TensorFlow, right? So that's what the name of the live stream. So once we've imported our dependencies, we're going to import our data set, okay? So TensorFlow, luckily for us, has MNIST beautifully packaged for us, and we can just import it. We could just import that data set. There's no if, and, or but. There is just data. When it comes to this stuff, it's easy. We just say input data. We've already called it, and then we can just read it with this read dataset function. The read datasets function, given the location of our data, which is going to be in temp data. And then we say one hot equals true, which means we want to one hot encode it. What does that mean? It's a way of encoding data such that it differentiates it without ranking them. So then what happens is I get an error. So that's the next step. So then what I've got to do is I got to make sure it's plural. There we go. Boom. So we've got our data set, because we don't care about the data really. We care about this model. What does it look like? So let's go ahead and define some parameters here. Well, the number of pixels, right? MNIST, these are a set of handwritten character digits. They're 28 by 28 pixels for the image. So I'm going to say 28 by 28, this is the number of pixels, and we're going to use this as a parameter when we define our tensors, right? So let's go ahead and say, let's define our placeholder. And what is this? This is an unsupervised learning problem. We don't have labels for this data, or we do, but we don't care about them in this case. We're going to learn to reconstruct our input images given our just our input images, just given that alone. So we're going to say tensorflow.float, and so this is our placeholder, right? This is what we're feeding in our initial values. Okay, so x equals tf.placeholder, tf.float. Good, we got the good stuff. Now let's go ahead and define some variable or some functions here. So the first one is going to be the weight variable. So by the way, this is for our input the images. This is our gateway, right? Remember, placeholders are gateways. And yeah, so weight variables. Okay, let's get started with our weight variables. So the weight variables are going to represent the strength of connections between our units here. So given some shape, which is a tensor, and some name, we're going to create weight variables. So the reason we're defining these functions here is because they're an easy way for us to reuse what is going to be used for as many layers as we have. This is good practice to encapsulate your logic that you think is going to be reusable into functions. Okay, so that's just OOP, object-oriented programming. And so then we've got our good stuff. So truncated normal, it outputs a random value that's either going to be bounded. Truncated means bounded, so it's going to be bounded between some set interval. Okay, and so the standard deviation is going to be 0.1. The deviation is how far off from the mean does it move. Okay, so that's going to be our weight values. That's it. Those are our weight values, and then we could just return that as a variable because TensorFlow works with variables. So we'll add initial to our variable, and then we're going to give it a name that we're going to name it outside of the function, and then it goes into the function like it does. Okay, so then we've got our biases. So biases are actually not that well understood. There's not a lot of great explanations around why we use biases. It's just kind of like, you know, hand wavy. Oh, and then we have our bias, and then the cows come home. That's actually a bad analogy for this. But what happens is we need biases because they are used to increase the flexibility of the model to fit to the data. They prevent overfitting. They're like an anchor. They're like an anchor point. So, you know, y equals mx plus b, the equation b is the bias because it moves, it translates a graph, right, across a plane. And they allow us to fit data even when an input value is 0. If an input value is 0, then if there wasn't a bias, it would just output 0. But since there's a bias, there's some constant value there. We have some value that we could continue training. So it prevents overfitting, and it increases the flexibility of our model to fit to the data. Specifically, it allows the network to fit the data when all the input features are equal to 0, which is what I just said. Okay, so I'm gonna answer questions once I finish this good stuff. So we've got our truncated normal, and the truncated normal, it's also going to be it's going to be generated randomly, and then we're going to return it as a variable. Variable is a modifiable tensor, and yeah, these are primitives in TensorFlow. Guys, isn't PyTorch so dope though? I'm definitely going to make a video on PyTorch soon. Not that TensorFlow isn't also awesome, but there's some good stuff coming out of PyTorch recently, seriously. So we've got FC layer. So what is this? So we've got our weights, we've got our biases, and now we're going to create a fully connected layer. A fully connected layer is one where all the neurons on the input are connected to every neuron in the output. Okay, so that means we want all of the data. And what do I mean by, like, you might be thinking like, well, don't we always want all the data? Like, when else? No, because sometimes we only want part of the data. What would be a good example of this? Convolution. It's convolutional networks. If we have an image of, say, a banana, we don't care where in the image the banana is. We just care that there is a banana. So what do? We don't use a fully connected layer. We use a convolutional layer that acts as a flashlight, and it slowly moves through the image until it finds that banana, and it only uses that part. Why? Because it's computationally efficient. Okay, so given our fully connected layer, what we don't want that in this case. We want a fully connected layer because We are not labeling data. We are generating data. So we want all of that image. Okay, so because we don't know what it is that we want. We're not classifying anything. We're generating. We don't care if it's a banana or whatever it is. Okay, so the fully connected layer is going to do a matrix multiplication between the input, the weights, and then add the bias. It's like y equals mx plus b. It's the same thing. So those are our 3 layers that we have. Okay, so yeah. Those are our layers. And now let's start writing out our encoder. So before we start writing out the encoder, answering questions. Let me answer some questions now. What do we got? We got 4. Wow, we have even more people here. Yes, I did a video on TensorBoard. Yeah. Great. So, Prabhat Mohanty says, please do a comparison between TensorFlow and MXNet in your style someday. I'll consider it. Aditya says, difference between RBM and an autoencoder, please. So RBMs, that's a restricted Boltzmann machine. And those are used, I mean, to me, the coolest use case of RBMs are in generating music. They're more similar to Markov chains than to autoencoders. Autoencoders reconstruct. They're meant for image compression, whereas RBMs are from the start meant for generation. 2 more questions and then we'll get started. Prashant asks, is it possible to make multi-layer autoencoders learn to completely repeat in? Completely repeat. I'm just going to paraphrase. Probably what you're saying is to reconstruct the input. Yes, they are. 2 more questions. Does dropout reduce overfitting? Yes, that's the point of dropout. That is the point of dropout. When somebody is overfit, their minds are too closed. So how do you prevent closed-mindedness? You add new experiences. You have some kind of new experience, and then so dropout is akin to that. It is opening and closing connections randomly so that new synaptic connections can be made. All right, and then the last question is, does it make any sense to use 2 FCs to run in parallel and they combine at last, give output? Does it make any sense to use 2 fully connected layers to run in parallel and then they combine? So no, for sure. I mean, you could run them in parallel. Distributed TensorFlow is a thing. We haven't actually talked in detail about that, but yeah, it's definitely a cool thing. Yeah, for sure. So yeah, anyway, back to the encoder. So we've defined our functions. Let's go ahead and start putting them to use by defining our encoder, right? This is what our encoder looks like. We've got our input, encodes it into a latent space, and then we output it, all right? Simple stuff. We've been talking about this. Let's go ahead and get started with our encoder. So encoder time, guys. For our latent dimensionality, so it's going to be 20. So what do I mean by latent dimensionality? So when we have this latent space, this representation space, we want a certain number of dimensions, right? And what are those dimensions going to be? Let's say 20. Now, should they ideally be 20? Why not 21? Why not 19? We're just going to try 20. A lot of machine learning is guessing and checking these hyperparameters. So we have a latent dimensionality of 20 for this latent space, and then a hidden dimensionality of 500. What do I mean by this? This means 500 neurons in that input layer. So let's go ahead and say, define layer 1. This is going to be a 2-layer feed-forward neural network. So let's just define our 2 layers. We have our first set of weights, and now we're going to use those variables that we just defined. We just defined them. And the number of pixels and the hidden dimensionality, this is going to be the size of our tensor. We want to make sure and that's why we define these things, because we want them to be in a size that fits our tensor, and then we're going to name it, okay? So that's our weight, that's for our weights, and then for our biases, right? So each layer has its own set of weights and its own set of biases. And we have our hidden dimensionality and then our B encoder. Okay, so right, there we go. Boom. So that's for layer 1, and then, oh, we have one more step here. But okay, so this is the fun part. I'm just gonna write tan H here and then explain what I'm talking about, right? So we've got some input data. We put it through the weights and the biases, and well, we need to compute something, right? We need to compute something. So to compute something, we're going to use a tan H function. So what is tan H? So this is our fully connected layer, given the input data, and then those weights that we just defined, and then those biases that we just defined. We're going to compute some output value. And then we're going to feed the output value to this activation function that is tanh. So tanh is our activation function. Okay, so weights, encoder, biases, and XFC layer, it's all good. Okay, so the tanh function is considered the hyperbolic tangent function, which is similar to sigmoid, except the range. So sigmoid's range is between 0 and 1, whereas tanh's range is between -1 and 1. So it's a larger range. And when do we use it versus sigmoid? So there's actually a lot of theory behind activation functions and when we use it, but in this case, we're just going to say it avoids the vanishing gradient problem compared to the sigmoid. Not in all cases, but when it comes to generative models, tanh avoids the vanishing gradient problem. Why? There's a whole bunch of reasons behind that. We don't have time to go into all that right now, but let's just say it avoids the vanishing gradient problem. And this is a problem in all neural networks, okay? No one is safe. No network is safe, okay? So whatever we can do to prevent that, we're gonna do. All right, so this next layer, we could actually just copy and paste this because it's, it's the same thing more or less. MU, and then MU. What do I mean by MU? Mean, okay? MU stands for mean, and then we're gonna rename it, and then I'm gonna answer, no, well, actually I just answered some questions, so I'm just gonna keep going here. MU, biases, and then I'll call it what I just called it. Do what I do. I do what I do. I do what I do. Oh man, okay, so X, right? It's all good, right? It's all good. You guys gotta keep me in check. You guys gotta keep me in check. You guys gotta keep me in check. I love reading your comments. You guys are hilarious. Okay. See, what I love about you guys is that you help each other out. That is a culture that we are trying to create here. Okay. So those are our two layers, and so now is the dope part. Okay. So this is what makes me really excited. So we've got our two layers, and then generally, I mean, normally that's it, right? It's just we wipe our hands clean, drink some coffee, do whatever you gotta do, go home, play GameCube, not GameCube. But in this case, what we're gonna do is we are going to, normally we would output a vector of real values, right? And that's it. And then we use backpropagation like we always do. We compute the partial derivative with respect to the weights given our error value, and then it's all good, right? It's all Gucci. But in this case, we have randomness built into the model, so we can't just backpropagate normally. We've got to perform a trick, a reparameterization step, and I'm going to talk about what I mean by that. So, what we're instead of outputting a vector of real values to this hidden state, we're going to output a vector of means and a vector of standard deviations. And then we're going to have a random component, okay? And so when we backpropagate, we're only going to backpropagate in relation to this mean value and this standard deviation value. We don't care about this random value over here. Why? Because we can't take a partial derivative of a value that is random, that is not predetermined. The mean and the standard deviation are predetermined values. So of course we can backpropagate, but a random value, we can't do that. So what we do is we separate the random value. We put it off to the side. We say, all right, you just sit there. It's all good. You just live your life. And then we have this mean and we have the standard deviation, and that's what we backpropagate with. Okay, so I'm going to show you what I mean by this. So what we do here is I'm actually going to wait a second. Let's see. So for layer two, oh yeah, so there's no tanh function here. So for layer 2, there's just the FC layer. Okay, because this is the mean value. So this is the mean value. So we're not going to perform that activation function. We just, if we did that, it wouldn't be the mean, right? So we've got that layer, and then we've got our log std layer. Okay, so we just do this twice. So this is going to be for our standard deviation. So let's just call it std. And then what we're going to do is we're going to say w log std. So they also call it log sigma in a lot of repositories. They call it log sigma. But what we say is we say log std, and w log std, b log std, and we name it properly. Because remember, we got to make sure that the names are all good. B log std, all the names, all the good stuff. Always low prices. Wait, that's something else. Okay, log std, and then h encoder. Let me make sure that it's all good, because you got to do this, right? You can't just compile some BS. So FC layer, yep, okay, latent, yep, bias, W, yep. Oh, no. And then latent. You got to make sure that it's all good over here. Okay. Yeah. Oh, see, I missed some stuff here. Okay, so we've got our encoder, and now we're going to write out our decoder. Who's ready to write out a decoder? Oh, actually, before we write a decoder, we got to write out our step here, right? Okay, so here's a step. So this is, I'm gonna write this out in all caps, by the way, because it's that important. Get ready for this. If you haven't been paying attention, if you haven't been awake, wake up, because it's time for the randomness. The randomness, see how many times I wrote that S? That's how important this is. So what we're gonna do is we're gonna say noise equals tf.random normal. So we're gonna create a random normal distribution. And then we're gonna say, well, what are the intervals that we want to generate this random normal distribution? This is our randomness. This noise, this variable right here is a randomness from which we're going to take this randomness and we're going to, let me just show you what we're going to do with it. So we have our mean and we have our standard deviation values, and we're going to say Z is going to be our ultimate output. So Z is our ultimate output. So Z is the ultimate output of our encoder that we then feed to our decoder. So what we care about in the end is Z. That's the output. So given our value, so we have our mean. So we take our mean and we add it to the multiplication to the product. I blanked for a second, of our noise and our standard deviation. And we're going to perform this exponential step by taking half of the standard deviation, and that's going to be our step. Ultimate output of our encoder. Okay, so when we backpropagate, we care about these two values, okay? The mean and the standard deviation. We don't care about the noise, but the noise helps us generate Z because we multiply it by the standard deviation plus the mean. So it's adding randomness to this output without affecting backpropagation, which is perfect. How beautiful is that solution? It's a beautiful solution, isn't it? So this lets us backpropagate, and the less information that we pass using that one variable, the more efficiently we can encode the original image. Okay, so the higher we raise the standard deviation on our Gaussian until it reaches 1. Okay, so this constraint forces the encoder to be very efficient. So because we are looking for efficiency here. Okay, so that's it for our encoder. And let me make sure that okay, so let's see what we got here. Weight variable is not defined because I called it weight variable. Wait, did I even, variables, that's what it is. Weight variables. Okay, there we go. All right, so, okay. So we've got some errors. So we've got weight variables is not defined. Oh, because I renamed it up here. That's why. Yeah, great. Yep. FC layer is not defined. I definitely define FC layer. I don't know what you're talking about. Oh, because it's lowercase, right. Guys, this is the thing that happens when things happen, right? Things happen when things happen. Okay. We're getting closer. Watch the debug. It's all about the debugging in the end. Mean. What are you talking about here? What you talking about, Willis? What do we got? We've got dimensions must be equal, but our 784 and 500 for matmul. Oh, okay. Well, okay. Let me answer some questions as well. While we talk about, and let me see what people are saying over here. Programming woes. Yo, we've got even more people. This is a record right here. Can we use an autoencoder to detect anomalies in time series data? That's a good question. I wouldn't use that. I would use k-means, which I haven't talked about, but I will. Spoiler, but I will start talking about k-means and more generic machine learning algorithms. But I wouldn't. What's this second layer you just wrote? Same weight dimensions as the other layer? Yeah, same weight dimensions, except we are not applying an... Yeah, exactly. The second layer is the same dimensions, except... Okay, let me just... I gotta paste this one in because we gotta keep going in. What is this? This is something else. There's so much. These are all my notes. There's so many notes here, aren't there? So if in terms of documentation, I mean, this is the most documented code I think I've ever written. So that's going to be a treat for you guys, okay? So where were we? I was answering a question here. And I wanted to make sure, there are so many different things happening here that I want to make sure that what this guy asked is, so the second layer is going to have a fully connected, so it has a fully connected layer at the end of it, whereas the first layer does not. The first layer applies an they both have fully connected layers, but the first layer applies an activation function to it, whereas this next layer doesn't, because if we applied an activation, then we wouldn't get a mean value. And we need a mean value. We need a mean and we need a standard deviation value as a way of representing the computations that happen in the encoder, okay? So, oh my God. Oh my God. Okay, so we gotta say, nope. Eventually, we're gonna compile this. Eventually. It worked. Hallelujah. Okay, so decoder time, guys. 2 more questions and then decoder time. Okay, Ricardo Molero asks, would it be possible to develop this model with simpler TF code like tflearn.inputData, tflearn.fly? Yes, absolutely. No, yeah, Ricardo, I'm doing it in Tensorflow because it's more intensive and this is a longer session. But if you look at my weekly videos, Keras, it's all, you could do this in 10 lines, yes. You could do this with an API with 1 line, but we're trying to learn, you know, a lot of stuff here. Okay, what's the difference between a usual denoising autoencoder and a variational autoencoder? Denoising, there's a lot of differences, but denoising autoencoders don't have stochasticity built in. So they don't have this reparameterization step that we just performed. One more question. Is it possible to use symbolic language to show or try to figure out how the model works? Symbolic language. Symbolic language could mean a lot of things, but yeah, symbolic language to show how the, so one way of thinking about this is in terms of computation graphs. So if we think about what the computation graph looks like, so PyTorch is actually a great resource for that, because what you write versus what you see on the graph, they look very similar. It's not different. So PyTorch. Actually, one more question, because I'm just kind of, what is latent space? Latent space is the representation of what we've just learned, a lower dimensional representation of what we've just learned. Latent equals hidden equals embedding. That means the same thing, okay? So decoder time. So for the decoder, we've got that embedding, and now we're going to reconstruct the embedding. And I'm going to okay. So let me open something else. I'm gonna open up one that already had. I'm just estimating time here. So what I'm gonna do is I'm going to say, I'm gonna open up my exact same notebook, except it's got all the code already there, and which is what I'm reading off of, by the way. And I'm just, because we need to explain what the decoder looks. So for the decoder, we have two layers. So it's also a two-layer feed forward network, just like the encoder. And if you so let's go by this line by line, okay? So line 1 is we define our weights for layer 1, okay? And then we use the latent dimensionality, which is 20, and the hidden dimensionality, which is 500, which is the number of neurons, to define what the size of this weight variable, which is a matrix, what does that look like? Then we say this is our bias variable. And so our bias variable is going to be much smaller. It's only going to be the size of our hidden dimensionality, which is 500. And then what we say is, we say, okay, so given our weights, given our biases, let's then define our hidden layer. Let's define the actual layer itself. So we say, this is going to be a fully connected layer. So layer 1 is fully connected. They are both fully connected layers. Both layer 1 and layer 2 are both fully connected layers. And this is how we define it. We say our fully connected layer gets our Z, which is the output of our encoder. This is where Z comes in. What we just calculated with the reparameterization step is right here. Given our Z, given our set of weights, given our set of biases, compute the fully connected layer. It's going to output a set of, that set of values, a vector, that we then squash with our dimensionality, with our activation function, which is going to be tan h, our hyperbolic tangent. And then that's going to be the hidden state values, and that's stored in H hidden decoder, okay? So that's layer 1. And then for layer 2, we say, okay, we've got those values, and we want to feed them into our next hidden layer. So again, we're going to call this reconstruction, okay? And this is important because we're going to use reconstruction later when we generate novel data points. So we say W reconstruct, B reconstruct. These are our weights and biases for layer 2, and then we say for our fully connected layer, we'll use both of those terms to then output a vector of values that we then squash with a sigmoid function. And so why do we use a sigmoid function versus a tan h function for this last step? Because a sigmoid function is going to output a set of values between 0 and 1. These are Bernoulli parameters. What do I mean by Bernoulli parameters? Because in the end, we just care about if something is real or fake, right? That's a binary output. It's a binary classification. And a Bernoulli distribution only outputs values between 0, or values that are either 0 or 1. They're binary output. That's what we call Bernoulli. So Bernoulli is just a word for this. But to be technical about it, it's considered 784 Bernoulli parameters, which means 784 values between 0 and 1. Okay, and that's going to be the reconstructed image. Right? And so that's what sigmoid helps us do. It turns us those values into values between 0 and 1. And so our reconstruction, this is our reconstructed image right here. This is this set of values stored in here, okay? So that is our reconstructed distribution, okay? So let me answer some questions, and then we're gonna get started with our loss function, which is going to be amazing, okay? So questions we've got are, why are we calculating mean using FC layer? Right, so why are we doing that? Because the FC layer is going to give us a mean if we don't apply an activation function to it. Sadiq Omar asks, how do you handle time series data labeled in? So for time series data, you would want to use a recurrent network, and you would just, the labels would be the targets and the expected output, and then you could use something like mean squared error to do that. I've got a great video on that. See how to use TensorFlow for time series. Could you also, so Matt Campso asks, how do we cluster the latent space? I assume we take Z and then what? That's a great question. So the latent space, we can actually visualize that with Matplotlib, which we will do. And it's going to be clustered already. It's going to self-cluster. It's going to self-cluster. And we could just read that visually as humans and then see like, oh, all these data points are related over here. So for MNIST, clusters are going to happen, and this is a great lead-in question to what I'm going to show you. For MNIST, clusters are going to happen around numbers. So all the ones, all the representations of the one, all the images like of the number one are going to be represented together here. And then all the twos are going to be here, and then threes, right? All these images are going to be clustered together in a similar space, in latent space. Okay, so that's a great leading question to us defining our loss function, and you'll see why. So now we've got our generated, our generated image, and we want to compare the generated image to the actual image, right? So how do we want to compare that, right? Because if we go back all the way up here, what is it we want to do? We want to use a loss function to minimize the two distributions between the generated data and the true data. And so what we do is we say, this is what our loss function looks like. So get ready for this. So math time. This looks kind of scary, doesn't it? Because it's not in plain English. Math is an entirely different, beautiful language that we have to get used to. We just have to get used to it. It just wasn't taught well in school. We're going to redo all of that. Okay, we're going to redo all of that. Okay, math teachers were so boring. Most of mine were. And they really didn't show the beauty that math is. Math is so beautiful. Okay, so let me show you guys what I'm talking about here. So what we have here are three equations, right? These three lines of all of these symbols that represent constant terms. These are laws. These are rules that we found to always output the same thing, right? Given some set, it's really all the same thing. Given some set of inputs, we can always output a set of outputs. So here's what this looks like. So what we have here are a set of inputs and outputs. So what we want to calculate is the variational lower bound, which is what this first equation is. It is the variational lower bound. And it consists of these two other equations. So if we take these two other equations and combine them, that's what this top equation is. So this top equation is called the variational lower bound. And how do we calculate it? Well, we take the log likelihood, the second value, minus the KL divergence, which is this second value. So see how this first value says log P x probability of x given z. What is the log probability of x given z minus, and so we see it up here, right? Minus the KL divergence term. And I'll talk about what each of these mean. Okay, so the variational lower bound is what we want to minimize. That is our final loss function, and that's what we call the combination, which is really the difference of these two terms. So let's talk about them in order. So the first one is called the log likelihood. So what do I mean by log likelihood? So for the log likelihood, it tells us how effectively the decoder has learned to reconstruct an input image x given its latent representation z. So how effective is it? How well did we compare these? How well does this new distribution, right up here, compare to the old one? We want them to be very similar. And these are high dimensional distributions, right? But we can just think of them for our sake as just that bell curve. We want them to fit. We want those two bell curves to look the same, to be merged, so that if you were to plot one on top of the other, you couldn't tell the difference. It would just be an outline. So that's what we want. And that's what this term gives us. Okay? That's what the log likelihood gives us. Okay, so, and we can write this out programmatically, right? So the log likelihood is going to be the log probability of x given no, that's the KL divergence term. So let's see, let me go down here. I gotta make this bone bigger. So let's start off with each of these terms. Okay, so we've got the sigma. Sigma means that we have some set of values. So we're going to continuously perform these operations as a set. So we're going to say x times the log of y. And so we'll write this out programmatically. It's all the same. It's just a chain of operations that's going to give us this log likelihood. So we say x times the log of y plus 1 minus x times log of 1 minus y. And then we can write this out, okay? And I'll show you that. And so this next term is the KL divergence term. So for the KL divergence term, if the encoder outputs of those representations of z are different than those from the standard normal distribution, it's going to receive a penalty. So it's a regularization term. That's what we call it. Because if we didn't include this, the encoder would learn to cheat and give each data point a representation in a different region of Euclidean space. Euclidean space is the same as latent space in this case. It's just the same thing. So if we didn't use this regularization term, then if I wrote a 2, and that's an image, and I fed it to the model, and I encoded it, and it would plot it in representation space, it would be over here. And then if someone else wrote it, let's say Jeff Dean wrote a 2, okay, and then encoded it, and then we plotted that. If we didn't use a regularizer, then both representations would be far off. It would just be like over here and over here. But we don't want that. We want them to cluster. And so that's what this does. It makes sure that the distance between two values that should be very close together is small. That's what the KL divergence does. The full name of this is the, what is it, Kolbach-Leibler divergence, something like that. And so the KL divergence, that's what it does. It minimizes the distance between these 2 points so that they're clustered together, which is what we want. So both of these equations do two respective things for us. The first term, the first equation, the log likelihood, is going to make sure that our reconstructed image is similar as possible to our input image. And the second term, the KL divergence, makes sure that the values that we encode are close together in hidden space, in latent space, okay? So that's what both of them do. And if we take both of these terms and we subtract them, and these are, right, so the value on the left is what the entire equation equals. So we'll just use that over here. If we just subtract both of them, we'll get the variational lower bound, which is what the ultimate loss function is, okay? So, what this is going to do is it's going to let us use stochastic gradient descent, which is a standard backpropagation technique. It means backpropagation with respect to the variational parameters. Those are the mean and the standard deviation. Okay, and so this is what it looks like programmatically, right? And what we did here is we just wrote out each of these values and operations. So if we were to look at that, what can we look at here? Let's see. So for log likelihood, we'll say x times tf.log of reconstruction plus 1e minus 9. And what is it? X times log likelihood y minus e. See, it's the same thing, right? It's the same exact thing. Plus 1 minus x times tf log, but 1 minus... So you see how it's the same thing. Like, we're just literally number by number, operation by operation, we're just writing it out programmatically, right? Anyone can do this. It's not hard. You just have to get used to these symbols. They're just symbols. Okay, they just represent something. And for some people, actually, it's easier to look at the code and for me, for example, it's actually easier for me, to think about mathematical terms if I look at it programmatically, because I'm programming anyway. I'm not writing out equations anyway, okay? So, but these are standard terms, and you'll see them a lot in papers. Also, on a side note about math, when you see just chains of equations in papers, it's easy to get afraid because we haven't learned to represent these equations in more condensed terms. So usually what you're going to see is you're going to see a condensed version of an equation, and then you're going to see the long form. So you're going to see all of it. And so like this sigma term right here means the sigma term, so this equation right here could actually be written out by lots and lots of equations, but we use the sigma term to represent it, okay? So those are our terms there. And so, right, so we've written out for the KL term, the log likelihood, and then we use our variational lower bound, which is log likelihood minus the KL term, and then we use the mean value of that. And then we use our optimizer. So we're gonna use a negative value here because it's a little quirk with TensorFlow, whereas if you were to use a positive value, it wouldn't minimize it, it would maximize it. So we're gonna use a negative value to offset this quirk in TensorFlow. And I've recorded that in the GitHub, in the README. Not in the README, but in the code that you have. Okay, so yeah, so that's our term. And we're using, what was it? We're using Ada delta, which is a form of stochastic gradient descent. And yeah, okay, so let's keep going with training. So now, we initialize our variables, we've got our saver function here, and then, let me answer one question, by the way. What are people saying here? Bernoulli, okay? Oh my God, this is one guy who's like, I'm Italian and I have to say it. Stop using hands. It was the funniest comment. Okay, So, okay, 2 questions. And there's a lot of good questions. Could you consider doing NLP for text mining using deep learning and Word2Vec and topic model to automatically classify unstructured text? You would use NLP for text mining. That's a good thought. Using deep learning, that's a even better thought. And Word2Vec, yeah, I actually did this in a video. What was it? Word vectors using Game of Thrones. So search Siraj, word vectors, Game of Thrones. Okay, that's it. All right. Right. So okay. So for training, we're gonna say okay. We're gonna import time to clock our training time, and we're gonna say okay. We want 100,000 iterations, and we say our recording interval is gonna be 1,000 because we want to print out things every 1,000 intervals. And so we have these 3 arrays just for us for our logging purposes. They don't do anything like for the actual computation. They're just for us to log our values over time. And so then we say, okay, and same for our iteration array. It's just for us for logging. And so then we say, okay, for all of those iterations, and we're going to feed data into our model in batches, like we always do, batches of 200, so 200 images in a batch. We're going to say, okay, so this first batch, we're going to and we're going to use a round function to make sure it's binary, feed it into X batch, and then this is how we feed it into our model. We say session.run, give it our optimizer, feed dict, and we always feed it in a dictionary, X batch. And there's no target labels, right? This is unsupervised learning. There are no labels here. Okay, so then, and this is where, and then every interval, every 1,000 iterations, we're going to print out the values that we are in for all of these terms here, okay? And so then when we train it, so you see it's training right now. It's going to take a while, but let's wait for it to train. Let me answer a question while it trains. So another question before we get started with the good stuff is make a video on basic pandas data set. All tutorials are already processed. Any book recommendations for ML? Yeah. So the deep learning book by Bengio. Actually, just to really condense what I'm asking you to look at. So yeah, it's training, right? Stop training. That's going to take, it's on my MacBook. It would probably take like 6 hours to train this. Just read that math chapter, that first math, like what is the math needed for deep learning? Like that's a great chapter. It's a great chapter. And I've got some great stuff coming out on that, but I'm not going to spoil you guys too much. So let's assume we've trained it and then we plotted it. And so this plot is why we collected those values in arrays so that we could plot the values of these 3 loss terms over time. And you can see that they are converging, they are minimizing like that, okay? Right, and so actually, so these loss terms should be going the opposite way. Like it should be going like that, not like that. So if we were to flip this, it should look like that because the loss is minimizing. This is actually increasing. And I think this is because we set the, remember how we set the variational lower bound to negative? I think that's why. But it should be going down. Okay, so then for our results, here's how we plot out our images. So we say, okay, so let's take some images from our testing set, and then we reshape it to 28 by 28 pixels, and then we say, okay, for a subplot, let's plot it, okay? And so that's what's on the left here looks like. Okay, so what's on the left here, those are our test images. And the ones on our right are our reconstructed images. So say, okay, reconstruction.eval feed dict x. So we take our test image and we feed it directly to that reconstruction layer at the very end, right up here, this last layer of the decoder. We feed it in directly using the eval function of TensorFlow. And we say, okay, so feed that directly into the X reconstruction, reshape it so it's 28 by 28, whatever it is, it's gonna be output of whatever set of values, and then plot it. And we can see how we've now reconstructed these values, okay? And so I haven't rapped in a while, so I'm gonna rap about something. So let's see, I've got 390 people. So let's see. For a rap, I'm just going to rap about variational auto. Actually, if I were to rap about variational autoencoders, then you would think that it's off, that I've planned something. So what I'm going to do is I'm going to ask one of you guys to say a topic, and I'm going to rap about it because the lesson is over. So the rap is here. So someone shout out a topic that you want me to rap about in machine learning or in deep learning while I answer some questions. So with this technique, is it possible to generate content textual basing and pulverized news about this theme in the internet? Good job for using that term, pulverized. But yes, you can create fake news. Absolutely. I mean, this has been done. Yeah. Don't rap in Hindi. What else? Rap about Mexican cartels. That's not relevant. I am a super noob. Come on, guys. Russian girls. Guys, that's not deep learning. I mean, it could be, it will be in the future, but I am waiting for a term, guys. Come on. CycleGAN. There it goes. So go for it. I got my DJ over here. There we go. CycleGANs, everybody. It's time for the cycle. Are you ready for the CycleGAN? Because we're gonna talk about CycleGANs. CycleGANs, it's like I do it when I ride my bicycle, man. I do it every day. I was talking about GANs, but right now, it's about to be VAEs. I'm like a clown. Wait, listen. I'm trying to listen to this beat. I'm trying to rap about generative adversarial neat. It's so cool when I do it. I've got networks that generate stuff like a fluid. You can generate new fluids. You could generate everything. You could generate anything that your mind thinks. It's all the same. You take some data. You learn a distribution, man. Man, it's like mu alpha theta in maths in high school. Remember that club that you were in every day, man? It's like a flub. Yo, anything that I said rhymes because it's like online every time. Okay, so that was it. Right, so thanks guys for showing up for this. And now we've got, what do we've got? We've got 100, we've got 375 people here. Thanks for watching, guys. And make sure to look at this stuff. The code is in the README. The code is in the GitHub repo in the description. I want you guys to start generating things. We don't have enough people generating cool stuff. We only have people generating MNIST digits and faces. Let's start generating some cool stuff. Let's start generating DNA sequences. Let's start generating like new fashion styles and just let's start generating entire 3D worlds and maps and just alternate realities and just things that you would never even imagine. Entire movies, we're going to generate all of that stuff. Okay, so thanks guys for showing up. Come and do a hit in Moscow. I would love to come to Moscow when I do go to Moscow. Hopefully I don't die if I go there. No, I'm just kidding. I love Moscow. I can't say I love it because I haven't been there, but I love Russian. Da не знаю русский, ты холодный славянский убийца. Okay. Yes, I know Russian. Da не знаю русский. You didn't expect that, did you? No one expects that. I actually know a lot of languages. Okay, so 7, in fact. Not including programming. Bye, guys. I love you guys. Thanks for now. I've got to go work on generative adversarial networks. So thanks for watching.